Hertz and Lennartz did a lot of experiments and studied this photoelectric effect, and they came out with some like fantastic observations.
Right.
And these are used like without even knowing about them. They are like they have become so commonplace that in this chapter, if we solve problems of photoelectric effect, we take this for granted and we do not even think about it.
Okay, so they're pretty much like axioms. It's like
Yeah, it's like we need to use these, but it's so useful, like it comes in everywhere, so that people think it's going to happen as well. So they don't really give credit to Hertz and Leonard that much, but these are used everywhere. So
okay.
we're going to study about that. So electrons are emitted only if frequency is greater than threshold frequency, or nu is greater than nu naught. Remember this, no matter what intensity is coming, if the nu, that is the frequency of the radiation, is less than the nu naught threshold frequency, no photoelectric emission is going to take place. And there is no time lag between incidence of light and emission of photoelectrons. Like if this is a surface and a photon of like required frequency comes and hits the surface and causes photoelectric emission, the electron would come out instantly. There will be no time lag.
Right.
This is in contradiction to the wave theory, where the electrons should have come out after absorbing sufficient energy over a significant amount of time. But the experiments suggest that this is not the case. The electron comes out immediately when the photon strikes it.
So this is when dual nature of concept came.
Yeah, there were several instances where a dual nature had to be introduced, because the wave nature or the particle nature in itself could not solve or could not explain the experimental observations. So next we go to the third observation here. Work function and threshold frequency will vary from metal to metal. That is, it depends on the nature of the material.
Right.
So this is fairly basic, because we know that for different metals they will have different work functions, and the same frequency of light may not cause photoelectric emission in all the metals. So work function and threshold frequency are different.
Right.
Then the energy of photon, as we discussed before, is h nu or hc by lambda, where nu and lambda are like the frequency and wavelength of
so this was a Hertz and Leonard's observation?
Yeah, it's
a pretty important formula by the looks of it.
Yeah, it is really important, and we have been using this in different problems, and we will be using it in all the problems here. So this was also stated by them. And then photoelectric current is proportional to intensity. This is where the intensity comes into place. Not when the photoelectric effect is going to take place, but the photoelectric current is proportional to intensity.
Okay.
So I'll explain how this is possible. Because suppose this is a surface and there are countless electrons here, and if suppose this is a light of lower intensity, it will cause photoelectric emission in a lower scale.
Yes.
If there is light is of higher intensity, then it will cause photoelectric emission in a significant way.
Right.
So the amount of electrons coming out would be more.
Yes.
So that will cause a greater
intensity.
Greater photoelectric current due to the higher intensity.
Okay. So photoelectric.
But the fact that we all need to remember is that the frequency must be higher than the threshold frequency.
Right.
No matter what the intensity.
Right. So they might ask conceptual questions based on these theory part.
Yeah, there might be a lot of conceptual questions, and where this intensity and frequency thing would be introduced, and it's like highly likely that people might get confused. But if the concepts are clear, we can easily solve those problems.
Right. So let's move on to the sixth part.
The sixth part is the matter waves and wave nature of particle.
Okay.
So here we get introduced to the de Broglie relation, which is very, very important for this wave particle duality. So lambda, which is the de Broglie wavelength, is equal to h by mv. H is the Planck's constant, m is the mass of the particle, and v is the velocity, which is also written as h by root over twice me E is the energy,
Oh,
m is
okay.
the mass, and 2 is a constant.
Right.
So this is basically mv, and root over 2me is basically the momentum of the particle. So here we get introduced to the duality, because lambda is a wavelength, which is a wave property, and mv or p, which is momentum, is totally a particle property. Earlier in like the earlier science concepts, if you would have said that a particle has both momentum and wavelength, people would have laughed at you. But since this theory came out, there has been a lot of like applications of this theory, and people have used this in a lot of things to explain a lot of things.
Right, but still for a fact we do not know how light behaves, right? It's not sure yet.
Yeah, it's not sure, because light is very the photons are really small, and it is very hard to do observations on them. And this is like, we do not use this thing for normal day-to-day observations, because if a ball is thrown, then the wavelength associated with it would be in the range of 10 to the power minus 30s or 10 to the power minus 25 or something like that, which is not really like significant. We do not need to consider such low wavelengths. But in case of an electron, it becomes really useful, because it comes in the order of 10 to the power minus 6, 10 to the power minus 10, like that. So in that case, we need to consider the wavelength, the wave particle duality. So here are some shortcut formulas that you need to remember properly to apply directly in many problems. For a charged particle, the lambda de Broglie wavelength is h by root 2me, which comes out to be h by root 2mqv. M is the mass of the particle, q is the charge on it, and v is the voltage applied to accelerate it.
Fair enough.
So for electron, I'm giving you another shortcut here. Lambda is directly equal to root over 150 by v. 150 comes after some calculations, and v is the voltage through which the electron has been accelerated. It gives the lambda in Armstrong.
Right.
Then we come to gas molecule. Though it says gas molecule, you can apply it for like neutrons as well, where there's a single particle itself. So lambda equal to h by root 3 mkt. M is the mass of the particle, and k is the Boltzmann constant.
Okay.
And T is the absolute temperature, that is temperature in Kelvin scale.
Right, because it's SI.
Yeah. Boltzmann constant is given as 1.38 into 10 power minus 23 joules per Kelvin. This is a constant that you need to remember, like the Planck's constant and all that stuff. You need to remember this, the correct value, and unless stated otherwise, you are going to use this value. And then the next part is the ratio of lambda of photon and electron. This question might come directly in your examination, so you do not need to do too much calculation. I'm giving you the formula directly. It is lambda p, that is the lambda of wavelength of a photon is hc by E, and for an electron it is h by root 2 mk, where k is the kinetic energy of the electron. We take the ratio and we come to this formula, root over twice mc square k divided by E square. M is the mass of the electron, c is the speed of light, k is the kinetic energy of the electron, and E is the energy of the photon. So simply substituting the values, you can find out the ratio of the lambda of photon and electron. Yeah.
Fine. So, right, this is pretty helpful. And do we move on to the next page?
Yeah.
Right. So, what are we teaching? What are we learning right now?
This is a basic theoretical concept about Davison-Germer experiment. This experiment was done by Davison and Germer for this wave particle duality. They used an electron beam, and they found out that the wavelength of an electron is the de Broglie wavelength is 12.27 divided by root over v. This root over v, the v is the voltage through which the electron beam is accelerated by applying the voltage between cathode and anode, of course. And there are scattering graphs which are plotted after this experiment, and we see that there are bumps in the graph when this v is varied, and this maximum bump comes when V is 54 volts and it is smooth below 44 volts. These are basically theoretical concepts where questions should be asked about this itself, and you do not need to have too much of calculations.
Right. So, what do we know? What do we keep in mind of this particular experiment?
For this experiment, you just need to keep in mind the first formula that I have given, lambda equal to 12.27 divided by root V. And then the rest is like fairly simple, and they will ask theoretical questions based on this, and that is given in many books, and you need to remember what the experiment was.
Okay, right. So fine, let's just recap from the first page one last time so that we can, yeah. So there was dual nature of radiation. We learned about a few formulae, particle nature of light, a few more formulae, and some concepts. Emission of electrons. We learned the different types of emissions. And then we went on to the next page where we learned a few formulae of photoelectric effect, and then also the Hertz and Leonard's observation as to what they observed in the experiment they made, and matter waves and wave nature of particles. So the basic concept of dual nature is that light travels or propagates as a wave and interacts as a particle. Finally, we came over here about the Davison and Germer experiment. So right now, let's solve a few questions and recap the theory again.